Hello and welcome to a virtual lecture about planetary atmospheres. So we know a lot about the Earth's atmosphere, but there's also other planets in the solar system. So there's the giant planets, there's Mars, there's Venus, and also some moons. And that can give us an insight into atmospheric processes on a more general scale. So today I want to talk about a large moon of Saturn, which is Titan here, which is the orange fuzzy blob just in front of Saturn's rings there. So what's interesting about Titans, if we look at the graph on the left, we've got a graph of temperature versus altitude, and the orange line shows the temperature profile measured from a probe through Titan's atmosphere. So what's great about Titan is it's almost got exactly the same temperature structure as the Earth's atmosphere, only it's a lot colder. So it gives us a kind of insight into processes in a terrestrial kind of atmosphere, but in an extreme environment. So if we look at the picture on the right there, we can see there's a lot of chemistry going on in Titan's atmosphere. So there's a lot of nitrogen and methane, and that gives rise to things like hydrocarbons and nitriles in Titan's atmosphere, which is a bit unusual. That's a bit different compared to the Earth, which has a lot of oxygen, but that gives us kind of a interesting atmospheric effects sometimes. So Titan actually takes a very long time to go around the sun. So it's orbiting around Saturn, and Saturn takes 29.5 years to go around the sun. And what's great here for Titan is that Cassini was actually orbiting around Saturn for 13 years or so, up until 2017 when it entered Saturn's atmosphere. So we've got almost half a Titan year worth of data here to look at to try and study what goes on in Titan's atmosphere. So when Cassini arrived back in 2004, Titan was in northern winter, so because it's very cold at the North Pole, we've got sinking air there, so these are the blue arrows in the north. We measured all the way round to southern winter or northern summer. So what we can observe is we can see how the southern winter polar vortex forms, and then we can compare that to the Earth, so it gives us quite a lot of insight into what's going on. So let's look at the southern winter vortex and see how that formed. So how do we actually do that? So we've got a space probe, Cassini, it's got some instruments on it. So what we can do is if we look at Titan's atmosphere, so if we look at the horizon of Titan's atmosphere, we can actually measure the profile of different gases in the atmosphere, so we can see how they change with altitude. So what happens on Titan with all this interesting photochemistry is all of that chemistry happens quite high in the atmosphere, as all the UV is breaking up nitrogen and methane and forming these crazy compounds in Titan's atmosphere. Once they form, they get mixed down through the atmosphere, and they eventually condense where it gets cold lower in the atmosphere. So what that gives us is a vertical profile through the atmosphere and a vertical gradient. So if there's any motion going on in the atmosphere though, so say there's sinking in the atmosphere, what that tends to do is it tends to drag the whole chemical profile down. So if we look at one particular altitude and there is sinking going on, we should see a higher gas abundance of these trace species than kind of anywhere else. So we can indirectly look for variations in the atmosphere and how the circulation changes. And this is very sensitive to very small motions. So using this technique, you can look for millimeter per second scale velocities, which is quite cool. So how do we measure these gas profiles? Well, we've got a spectrometer here. So the spectrometer we use is Sears on Cassini. So that's the picture on the left there. And that's about, the primary mirror there is about 50 centimeters across. So it's a reasonable size, but it's not a huge instrument. And what that does is we point at Titan, so in some plan like in the bottom graph there, and we can measure lots and lots of spectra like this. And in these spectra, we can see different emission peaks from various gases. So things like HCN, HC3N, CO2 and some hydrocarbons, so acetylene, for example. So what did we expect to see and what did we actually see? So if we look at the top there, we're looking at the South Polar region. So these are kind of a cross section. So we've got the South Pole at -90 degrees and the y-axis is the altitude scale. So what we would expect to see after sort of equinox in Titan's South Pole is we would start to see sinking due to the reducing temperatures lowering the atmosphere. So what that does is it drags air down from high up in the atmosphere. The air gets compressed as the pressure increases and we get a hot spot up in the high atmosphere. So this is this red hot spot that's forming up in the around about 2013. We would expect to see that as being very hot there in Titan's atmosphere. So did we actually see that? Well, if we look at the bottom, this is what we measured from Cassini. So we start to see a hot spot. So it starts to get hotter. 2010, it's getting hotter. 2011, it's getting quite hot. But then in 2012, the temperature really dropped and it actually got so cold that it was too cold to measure. So this was kind of very kind of different to what we expected. So some aspect of our understanding of Titan's atmosphere is missing there. So we need to investigate that. So this is another way to look at it. So if you look at the first panel A there, that shows the temperature profile and the different colors kind of go from blue to red and that they're kind of moving on with time from 2010, just after equinox. So that's the start of a winter in the south, up to 2016, just before the mission sort of ended. So we did start, if we look at the temperature, we did see an initial increase in temperature, but then very rapidly it gets very cold. So we kind of see what we saw in the previous graph, but in a different way. So maybe we can understand that by looking at some of the chemistry. So panels B, D, C, and E actually show gas profiles of some of these trace species. And what you can see is as time goes on after equinox, a lot of this gas is kind of advected down or sort of moved downwards by the atmosphere into the lower atmosphere. So it brings these high abundances at high altitude down into the lower atmosphere, which is giving us some clue to what's going on. And some of these enrichments are really huge, like factors of 1,000 or so. So how does that help us understand the vortex? So in a schematic form here on the left, this shows the South Pole. So we've got the South Pole on the right at -90 degrees latitude and then altitude. And then we've got sinking starting to begin. So in the top panel there, initially the sinking happens, driven by cold temperatures in the winter sort of pole at the bottom there. So that pulls the air down. We get compression, like you get in a bicycle pump. It starts to get warm. So that warms the air up at high altitude, around about 400 kilometers. And that's kind of what we expect to see. If we move to the middle panel, so kind of this unexpected region when it suddenly went from hot to cold in the upper atmosphere. What we actually think is going on there, which is quite unusual and kind of unique to Titan, is because we've got all these trace species that are really, really highly enriched. They actually are really effective at emitting infrared radiation and cooling that region. And that effect on Titan is larger than the effect due to compression. So it becomes cold and it's kind of very, very weird. But we kind of just start to understand this. So down at the bottom here, so a good 5 or 6 years after equinox, what's happened now is that the subsidence has really taken off. It's actually quite strong. So that compression effect in the upper atmosphere is now beating the emission effect due to the enhanced gases. So we're kind of seeing a lot of feedback here between the chemistry, the dynamics, and the sort of seasons. So it's very kind of unique to Titan, this. It's quite interesting. So I've just got a little video here to play of the temperature cross-section through Titan. So on the bottom there, we've got latitude from -90 degrees at the South Pole, which is where we're interested in, to the North Pole, 90 degrees there. And the pressure scale on the side there goes from kind of the bottom of the stratosphere up to the top of the mesosphere, and that's kind of increasing altitude. So this video starts in northern winter. So in northern winter, we've got subsidence. The North Pole is getting compressed, and there's the hot spot, that big red blob. So if we play this video now, we should see the temperature evolve with time. So you can see as the subsidence weakens at the North Pole, that hot spot decreases, it starts to get colder. Whereas if we look at the south, that's now becoming colder because it's going into winter. The subsidence is starting and the little hot spot started there. Now it's got very, very cold, so this is the anomalous cold region. And then as the subsidence picks up, the hot spot starts to reappear again at high latitudes there, which is just high altitudes, which is just what we saw kind of near the end of the mission when Cassini went and burnt up in Saturn's atmosphere. So we've got all this wonderful data now, so we can start to kind of figure out what that means in terms of Titan and in terms of atmospheres in general. So what can we conclude from this brief presentation? Well, Titan's a bit strange. It's got odd gases in its atmosphere, and when the winter pole starts and the vortex forms, you can get up to 1,000 times enrichment of those gases, maybe even more, which gives us some very odd effects. One of those is this unexpected cooling just after equinox, so, which is kind of suggesting a feedback between how much gas there is, the temperature, and the circulation in the atmosphere. So that's currently sort of moderately included in sort of climate models of Titan, but that obviously needs working so that the models can better agree with these observations. And beyond Titan, because Titan's kind of far away from the Earth, what can this tell us about Earth? Well, the great thing about looking at these other planets is we can take our climate models from the Earth that we think work, we can apply them to other planets, and we can see if they actually work on those other planets. And if they don't, maybe we're missing some key physics that we need to include. So all of these different planets in the solar system provide a really kind of stringent test of climate models. And we can use them as sort of natural laboratories to test out our understanding of climates and atmospheric processes in general. So as I mentioned, Cassini is now vapor in Saturn's atmosphere as it burned up in 2017, but that doesn't stop us doing more science on Titan. We've got amazing new telescope facilities like these ones at the bottom. We've got ground-based things like the Large Millimeter Array in Chile down there, and we've also got the James Webb Space Telescope, which is going to be a huge telescope that's going to be amazing for looking at these planetary atmospheres. So I hope that gives you a bit of a flavour of the kind of thing they can do by comparing Earth's climates to planetary climates. And thank you very much for your attention. Goodbye.